We established in Lecture 4.5 that any object moving in circular motion undergo acceleration by default, the so-called centripetal acceleration. Now in this chapter, we learned that for an object to undergo acceleration, there must be force. A force is needed to change the state of the motion of the object. This force causes the object to keep changing its direction as it travels along the circular track. Not surprisingly, this force which corresponds to centripetal acceleration goes by the name centripetal force. The equation to describe centripetal force is rather straightforward. If centripetal acceleration is given by v squared over r, v being the speed of the object and r the radius of the circular track, we learned how to derive this equation before, then centripetal force is given by mass times centripetal acceleration, which is equal to mv squared over r. The direction of centripetal force is the same as the direction of centripetal acceleration, that is pointing radially inward. I think this shouldn't be much of an issue for you to grasp. What I foresee is going to be an issue is that centripetal force, unlike all the forces we have learned so far, does not and should not appear in the free body diagram. Let me repeat that again. In solving dynamics problem involving circular motion, you can draw weight, normal force, friction, etc. on the free body diagram of the object. But you should not draw the centripetal force in the free body diagram in the same sense that you do not draw m times a in the free body diagram. Rather, you equate the resultant force which causes the object to turn to mv squared over r. This resultant force is the centripetal force. This resultant force may come from friction, weight, normal force, etc., which are drawn on the free body diagram. I will further illustrate this point through this example. How fast shall she swing the bob for it to make an angle 20 degrees to the horizontal, as shown in the figure, if the mass of the bob is 2.0 kg and the length of the string is 1.5 meter? As you can see, the circular motion of the bob around her dictates the presence of centripetal force. We have yet to identify what or which force is responsible for being the centripetal force, but we know for sure it has to be the force which points inward along the radii of this circular plane. So let us start by drawing the free body diagram of the bob. Go through the list of forces we discussed in the last two videos. Which of those forces are in action in this case? I identify two forces are acting on the bob, the weight and the applied force which comes from the tension along the string. Note that we do not draw the centripetal force. I do not draw the purple arrow in this diagram, although eventually we know it should be there. The plane of our interest is the purplish circular plane I showed you just now. This hints that we have to resolve our forces along this plane or perpendicular to this plane. In our case, weight has already been perpendicular to the plane, so we leave it as it is. Tension, however, is not aligned along the plane, neither is it perpendicular to the plane, so we need to resolve the tension force. It is clearly seen now that the horizontal component of tension force is the one taking the role of centripetal force. So this component of tension force will have to be equal to mv squared over r. Once again, I emphasize here, we do not include centripetal force in the free body diagram. Instead, we equate any force which is pointing inward radially after the free body diagram is drawn properly to centripetal force mv squared over r. For the expression of r, which is the radius of the circular plane, it has to be computed from our knowledge on the length of the string. Meanwhile, the vertical component of tension force balances the weight to ensure the bob to remain in equilibrium as far as vertical motion is concerned. That is to say, the bob does not go up or down vertically. To compute the speed is thus a matter of algebra. Notice how I'm making use the result from the vertical component, namely the equation for the vertical component of tension force, to substitute for t in the equation for the horizontal component. Interestingly, it turns out that the answer does not depend on the mass of the bob at all. To maintain either a 1 ton or a 1 kg bob to constantly swinging at 20 degrees below horizontal line, one will only have to ensure either bob to move at particular speed. And this speed is dependent on the radius of the circular track, or the length of the string if you wish. But of course, this exercise says nothing about the energy required to attain and maintain that speed. It does take much more energy for a 1 ton bob to attain the same motion as a 1 kg bob, obviously. The question asks for how fast the lady will have to swing the bob to maintain the given configuration. Fast could be interpreted in terms of speed, that is, at what speed she has to ensure the bob is moving to maintain such configuration. In that case, this solution is sufficient, and we can stop at this point. However, some of you may interpret fast in terms of frequency, that is, at what frequency she has to swing the bob. Frequency itself could be presented in terms of hertz, number of rotation per second, or RPM, which stands for rotation per minute. If you're thinking along that line, you are not wrong. In that case, there will be extra steps needed. Here we are making use equation we have learned before from the lecture on circular motion. The conclusion is that in terms of speed v, frequency is given by v over 2 pi r, and that gives us 0.69 Hz. If you wish, you could convert this answer further to rotation per minute. So I admit that the question is not very specific with what it wants us to compute. Well, I came up with the questions and I intended it to be that way. My point is, do not worry. Just put on your thinking cap. You are free to interpret the problem as long as it is still within reason. Besides, any real-life problem in nature hardly presents itself in well-defined manner, asking for specific solution. One thing for sure, it will definitely help if you explicitly write down your thought or interpretation of the problem on the exam paper so that I can follow your thought process.